Welcome to your Getting Started webinar for your Thinking Maps Foundations training. At Thinking Maps, brain research has always been fundamental to what we do. There are 6 key points we want to present to you about the current brain research and how Thinking Maps supports each one. Most of these concepts are not brand new, and we've talked about visuals, patterns, and higher order thinking for many, many years. You should have already downloaded the Circle Map note-taking guide prior to this webinar. So please take notes in this handout as you will be sharing key points you've learned from this webinar at the beginning of your Thinking Maps Foundation breakout session. So what does the current brain research state about brain-based learning? There are 6 key points we want to present to you about the current brain research, neuroscience, and learning. The brain is always changing itself as it learns and experiences new things. This process is called neuroplasticity, and that is the context that will frame this information presented today. Your brain will physically be different at the end of this webinar. So let's utilize what the brain naturally does. As educators, our goal is to help students make strong connections in their brains so they can easily retain and recall information and develop deeper understanding. The brain is built of neurons, and they communicate with each other using electrical and chemical signals. As neurons speak to each other, they create connections between them. When we create new experiences, it causes neurons to fire in a particular pattern. When we later recall that experiences, we cause those neurons to fire in that exact same pattern. And these patterns are how we form memories. The more neurons that fire together, the stronger connections are made. So these are the 6 key points, the 6 concepts of neuroscience and learning and how Thinking Map supports each one. Visual, based on a pattern that allows students to recognize their thinking, which is called metacognition. With automaticity, that supports social motion learning that allows them to deep sea dive into higher order thinking. The maps have been carefully designed to tap into the ways the brain learns and remembers information. Specifically, these 6 concepts in neuroscience are related to how the brain processes and encodes information, how it decides what is important enough to pay attention to and remember, and how it makes connections between ideas that are the basic for higher order thinking. So let's look at the first point, make it visual. Our brains are built to prioritize visual information. There's a saying that states a picture is worth 1,000 words. For instance, if I say, let's talk about what we know about elephants. What is happening to your brain right now is most likely you are seeing an image of an elephant in your brain, not the word elephant. All of us can recognize faces so much quicker than remembering people's names, and that's because the visual cortex is the largest and the most complex system in the brain. It has tremendous processing power, registering and interpreting as many as 36,000 images per hour. In fact, 90% of all information that comes into the brain is visual. The brain is an image processor, not a word processor. Images can help us store and retrieve information, make communication simpler and easier, and to comprehend and absorb complex information. Thinking Maps makes complex ideas visual. This grabs the brain's attention and activates the prior knowledge of their content, also the visual cortex, which is primed to process complex information. Adding words to the visual maps takes advantage of dual coding, using both the visual and language processing parts of the brain at the same time. This makes information more memorable and meaningful. The educational research focuses on the correct use of visuals. There are so many Blackline masters out there and graphic organizers, I'm sure all very helpful. But when it comes to visuals, the research is showing, based on Hattie's work, there is a hinge point that you see circled and on your screen. 0.40 is where we want to get our kids to. However, the effect size becomes significantly increased if students and teachers are using the visuals correctly. It gets up to 0.60, which is what we want in the zone of desired effect. We also have work by Robert Maizana who says non-linguistic strategies or dual coding, you will see a tremendous increase in student achievement. And even John Antonetti, who's known for his support in student engagement, he really talks about how thinking maps allow students to see their thinking in organizational ways. So if the research is showing that we need to be visual with our content and how we deliver information, the second key point is, what are the patterns? Our brains are primed to respond to patterns because we need in order to make sense of the world. If you look at the shapes at the top of the screen, which group of shapes do you think will be easier to remember and describe later? The patterns help us make sense of the world around us and makes it easier for our brains to encode new information, make abstract ideas concrete, and interpret complex information. So thinking maps makes pattern visible because they provide a structure for learning. More importantly, thinking maps also help students recognize patterns in information and see the big picture of how all the facts they need to know relate to each other. Because patterns are all about conceptual nets. Our goal is to teach our students how to be fishermen of information, and we can't do that without modeling how to use specific nets that are available. So if thinking maps are visual, based on patterns, then what is an example of a pattern or conceptual net? Here's an example for you right now, using informational text. It's about chimpanzees and humans. As you do a quick scan, I'm sure many of you are recalling moments where you have given students a highlighter. Well, what ends up happening is students highlight everything in one color because everything is important. Highlighters are a great tool. However, it just makes the words brighter. They just don't know what to do with the information. However, if we teach students the patterns, for example, these signal words are being highlighted in front of you right now. Words like alike, different, but. The purpose, the author's intent, is not just to tell you everything you need to know about chimpanzees and humans, but the mere fact that author used those key signal words shows you that this author is comparing similarities and differences between these two animals. Therefore, the visual pattern I need to take notes is this visual. This is called a double bubble map. Similarities go down the center and unique differences are on the outside. So if this is an example of one pattern, think about the power of teaching students how to take notes for close reading exercises. Now they know which type of fishing net is required to capture the essential information from informational text. So if this is the double bubble map and this is one pattern, what are the others? Which leads to our third point, metacognition. Metacognition is connected to the 8 core cognitive processes that you see in front of you, and here they are. From defining, to describing, to classification, to seeing analogies and looking at causes and effects. It just seems simple in front of you, but if teachers are using the same patterns in all content areas, it becomes wired into their brain. Because metacognition, based on Quigley's research, has shown that if teachers directly and explicitly instruct students how to think about their thinking, they become independent learners, not dependent students. And that's really what's all about. So the evidence has proven that if we teach kids how to think about it, over time, they'll be able to understand the concepts that's presented in front of them. So automatically, the 8 core cognitive processes of thinking maps already addresses the visual and the pattern component of brain-based learning. But there's also research that states that we need to teach students how to think. However, what does thinking look like? As former students ourselves, how many of you were told by your teacher, just think about it, but you had no idea what that meant? Now we can actually show students what thinking looks like. And this is what he talks about, the gap analysis. We know what we need to be doing because we know it's good for kids, but no one is showing how to do that is where the research is showing, and that is the gap. Well, thinking maps will fill that gap for you. Here's an example. An example of neural networking is being built as we speak. So with this visual, this is called a multi-flow map. When we use this visual, we use the cognitive vocabulary of cause and effect. But not only do we use that visual for cause and effect, there are other signal words we would use with the same visual pattern, like why did the author make that decision, or what motivated this character in this plot. A history teacher may say, what's the short-term, long-term impact of this decision? Or maybe a science teacher would say, what is the impact of violent weather? All of those key terms you see before you is related to that visual pattern called the multi-flow map. So think about this. When a student sees this visual in isolation, because it was presented directly and explicitly by teachers, now all these neurons will be fired together because it is a set pattern. But not only this, if a teacher just asks a student, what is the impact of violent weather? Then all these neurons will be fired together because it is a set. Neurons that fire together, that get wired together is our goal, because it really boils down to biology. Here's an example of a neuron cell. On the left-hand side, you see dendrites. Dendrites are part of the neuron that absorbs the neurotransmitters that's in your brain. It transfers those neurotransmitter into a nucleus that turns it into an electric charge. That electric charge goes down the axon, which is surrounded by a myelin sheath, a fatty substance. It's kind of like efficiency, like playing telephone. Once that signal gets down the axon, it goes to the axon terminal to the synapse. The synapse is the empty space between an axon terminal and a dendrite. So the very first time you learn how to text somebody on a smartphone, it took you quite a long time in order to figure that out because you're learning something new. But now you could text anyone with speed and ease because your neurons have fired so well together, it's done with automaticity, which leads to our fourth point. Building automaticity is the ability to do something fluently without having to think about it at a conscious level. The first time you were learning how to drive, it took tremendous amount of brain power to focus. Now we can all drive home without consciously having to think about where our feet go and when to use our turn signal or when to pop a clutch if you're taught how to drive a manual stick shift. This is our goal. Automaticity. Think about teaching students how to think independently with automaticity. Think about the power if all students in all content areas can become independent thinkers instead of dependent students. More time can be spent in deep sea diving into rich content that allows students to make meaningful connections. Here's a prime example of a quote from Florida, from Patriot Elementary School. Once students become fluent in using the patterns of thinking, a whole new world of content becomes less daunting to master because now they possess the visual tools to see their content in meaningful chunks. So when students feel successful tackling challenging concepts because they feel they have the tools to do it, that leads us to our fifth point. Tapping into social emotional learning. Emotion makes meaning. Success breeds success. If I think I can do it, I can do it. For example, when you are upset, your brain downshifts. That's why safe schools are critical to student success. When a student feels safe, they're more willing to take risks with their learning. Now think about this. Think about when someone insulted you and it took you 2 hours later to think of a good comeback. Because you're so emotionally charged, how do we think rationally? So think about this. When students feel that they are successful, they are more likely to pay attention to what's being presented to you because it comes down to memory. I mean, think about this. Where were you? What were you doing on August 14th, 2009? Unless it was a very specific date, probably none of us have any recollection what we were wearing or where we were that day. But I bet you can tell me exactly where you were on 9/11 or January to March and April of 2020. There are current unprecedented things happening in our country that attaches high level emotion to specific dates. So that's why when emotion makes meaning, it goes through this process. If a student is not emotionally connected to the content in a positive way, it gets lost. But if they attach meaning to it, then there's a higher chance to go to long-term memory. However, as it goes through long-term memory, those networks need to be built consistently. For example, learning how to ride a bike. You probably haven't ridden a bike in a while, but once you hop back on, it kind of comes back to you, kind of like muscle memory. Building positive associations with learning helps to strengthen memory. We're naturally inclined to engage with things that have positive associations and withdraw from things that have negative associations. And this is true for our students. The brains will not put anything into long-term memory, no matter how many times we ask them to read a paragraph or look at a flashcard, if it is not meaningful for them. Which leads to our sixth point. How do we stimulate higher order deep sea diving thinking? So what you have in front of you is an example of map combinations. This happens to be combo number 8. In our trainings, we present all 8 cognitive skills, all 8 thinking maps, but over time you will see immediately certain visual patterns work well with others. This is one of 8 because really what it comes down to is if a teacher is asking, what thinking map should I use today? They're just using it as a graphic organizer. The question educators should be asking is, how do I want my kids to think today? And then the visual patterns will come. Here's a prime example. Let's say in elementary school, you're teaching the concept about plants. So you really can't use one thinking map to teach students about plants because the content itself is so very dense. So instead of asking which thinking map should I use, the question we should be asking, how do I want my kids to think about plants today? So let's take it apart using a brace map. What are the parts of a plant? Transfer each part into what's called a tree map and take notes about the details of each part. Once students have gathered enough knowledge and built their schema base, then we can analyze the function of each part, which later leads them into scientific inquiry. What if the stem is damaged? What do you predict will be the effects? So in science inquiry, it's really about hypothesis and coming up with a conjecture. So you really can't just use one visual to teach this unit of study. It's really going to require all of them. Think about the power of teachers doing long-term planning in their content where they can visualize what the next steps are going to be. But let's say you're not teaching plants. Let's say you're teaching the digestive system. What a complex visuals you see in front of you. Any student can put those 3 words in a flow map: digestion, absorption, and elimination. But that doesn't mean they own the content, because students can put those 3 words in those boxes, but what you see below it that's color-coded is deep sea diving. For instance, if you know what digestion is, you should be able to tell me in your own words everything you know, then talk about the parts of digestion and the process right below it. That is our ultimate goal. So you may not need all 8 thinking maps or all 8 visual tools for every single lesson because it really depends on your objective and state assessments. So tapping into those 6 fundamental brain ideas has a cumulative effect that enables students to better encode, retain, and recall information to build strong connections between concepts for deeper comprehension. So just having thinking maps alone on a wall is not going to be enough. Students have to see the visual in a pattern in all content areas that allows them to think about their thinking, which is metacognition. So once they see these visuals in all departments, all grade levels, that's where the magic becomes. That's automaticity, where they're automatically going to see their thinking without having us prompt them to do so. Once breeds success, that's social emotional learning because emotion makes meaning. And once they feel they can, they will deep sea dive into deep content they're being asked to master. These 6 concepts in neuroscience related to how the brain processes and encodes information, how it decides what is important enough to pay attention to and remember, and how it makes connections between ideas is our ultimate goal. So thank you for attending this webinar today. Make sure you've downloaded all the handouts prior to your Thinking Maps Foundation training. Please use the link in your welcome email to make sure you have logged in and bookmarked TMLC, Thinking Maps Learning Community page. Download all the necessary handouts prior to your training. If you have any technical difficulties into logging in, please email support@thinkingmaps.com. Make sure you have your completed Circle Map note-taking guide ready to go so you'll be able to share what you've learned from this webinar in your virtual training. Here are your assigned handouts and materials required prior to the beginning of your training. Thank you so much for your time and attention, and have a great day.